Today we are going to start unit 4. First is Cauchy integral formula. First is Cauchy integral formula. Cauchy integral formula. Integral formula. Integral formula. First is the statement of this theorem. Let fz be analytic in a simply connected connected domain D enclosed by rectifiable Jordan curve curve C, and fz is continuous. Fz is continuous within C, then fz naught is equal to integral C 1 by 2 pi I fz dz z minus z naught, where z naught is lies within D. Fz is analytic in a simply connected domain D enclosed by a rectifiable Jordan curve, that is curve without multiple points, and fz is analytic within C, then this is given by fz naught is given by this formula, and this formula is known as Cauchy integral formula, where z naught is any point inside D. Proof. First, draw this figure. That is, this is our domain D, and C, this one, z naught is any point inside D. With z naught as a center, we will draw a circle or circle gamma of radius r. Okay, so write this: with at z naught, with center at z naught, we draw a circle gamma of radius r. That is, r is any arbitrary number. Next, equation of the circle is what is the equation? We know the equation of the circle. If z is any point here, then z minus z naught, magnitude modulus of z minus z naught, is equal to r. Put this equation 1. Next, we will define a function. Let us define a function. Let us define a function phi z as, next slide, phi z is equal to fz by z minus z naught. Okay, where this phi z is analytic in this region. In the region bounded by the circle and this curve, in this region our phi z is analytic. So write that, where phi z is analytic in the region Here phi z is analytic is analytic in the region bounded by bounded by bounded by the circle bounded by the circle gamma and the rectifiable Jordan curve and the curve C. Okay, we know we know from corollaries for multi-connected region multi-connected region that integral phi z over this circle is equal to integral of this function over this curve C. So write that is integral over C phi z phi z phi z is dz is equal to integral over gamma phi z dz. Okay, what is phi z? Phi z is fz by z minus z naught. Let's put the value of phi z in the integral c fz dz z minus z. Okay, so here gamma fz z minus z naught dz, where c and gamma traverse traverse traversed the traverse in anti-VRSE traverse in anti-clockwise direction. Next, from both the side of the integral, I am subtracting a quantity, then it will remain same. I am subtracting this quantity from both sides. I am subtracting this quantity from both sides. So subtract this quantity from both sides. In the next line, take integral common. We can take fz naught outside the integral sign as integral is with respect to dz. So write this gamma, and in the right hand side it will be gamma. Take integral common, then write the things inside integral. That is half z minus half z naught z minus z naught dz. Okay, put this equation 2. Next, putting z minus z naught is equal to r ai theta. That is the equation of the circle. This is the circle. We know gamma is circle, so equation of the circle is this. Take what will be dz? Dz will be r I e I theta. Okay, then d theta. Therefore, integral gamma dz z minus z naught is equal to, here gamma is a circle. Gamma is a circle, so its theta varies from 0 to 2 pi, and here dz is equal to r I e I theta d theta by r e I theta. So this cancel out, this cancel out, and this is equal to my 0 to 2 pi I d theta. So I will come outside. I will come outside, and this is 0 to 2 pi d theta, and this is equal to I 2 pi. So this is 2 pi. This one, that is integral gamma dz z minus z naught is equal to this one. Substituting this value in 2, we get substitute this value in 2, we get integral c fz dz by z minus z naught. Okay, integral c fz z minus z naught dz minus 2 pi I f of z naught. Here it is f of z naught, so put the value of the integral, we will get this one. In the right hand side it will be this one. Integral gamma fz, right hand side will left as it is, z minus z naught, and this is dz, and this is equal to, put this equation 3, not equal. Okay, since fz is continuous within c, fz is, and z naught is a point, fz is continuous, fz is continuous within this curve c, and z naught is a point inside c, so fz is continuous at this point z naught. So right, since fz is continuous at z naught, fz is continuous at z naught for epsilon greater than 0. By definition of continuity, for epsilon greater than 0, there exists delta greater than 0, such that f of z minus f of z naught is less than epsilon whenever z minus z naught is less than delta. That is for all point z naught, lies in this, we will get this one. Since r is arbitrary, put this equation 4. Since r is arbitrary, we choose h delta not h, delta greater than 0, since r is arbitrary, our radius is arbitrary, we choose delta greater than 0, such that 4 lies 4 is satisfied by all point gamma. Okay, 4 is satisfied, 4 is satisfied by all points in gamma. Okay, just fz is continuous of z naught, so it follow from the definition of continuity. This happens, that is this satisfied by all z, then we will get this one. Since r is arbitrary, we choose our delta in such a way that for this condition 4 is satisfied by all point here, all point here. Okay, therefore equation 3 become next, taking modulus, taking modulus on both side of 3, on both side of 3, side of 3, we get, this is the equation 3, this is the equation 3, so take the modulus on both side, we will get fz minus z naught minus 2 pi I f of z naught modulus, then in the right hand side it is a modulus of gamma fz minus f of z naught divided by z minus z naught dz. Okay, so again use the properties of modulus, properties of the this property of the integral, complex integral, we will get this one. Okay, using this property we will get this one, that is modulus of fz minus fz naught, okay, divided by z minus z naught, and this is your teacher. Rub this out. This portion is mine. From 4 we have this portion is less than epsilon. From 4 this portion is less than epsilon. Fz minus fz naught is less than epsilon. Okay, so I use this, that is in the right hand side we have, in the left hand side it will remain same, that is integral over c fz dz z minus z naught minus 2 pi I f of z naught, this less than epsilon, then here this is the, by using equation of the circle, this is the equation of the circle, z minus z naught is equal to r, this z minus z naught is r, so using that r, which is constant, can be taken out of the integral sign, so gamma dz. From the lecture of example for complex integral, we know this value is equal to length of curve. Here gamma, my curve is the circle gamma, and length of the circle is the perimeter of the circle, that is 2 pi r radius, and this is equal to epsilon by r 2 pi r. So r cancel out, this is equal to 2 pi epsilon. Since epsilon greater than 0 is arbitrary, epsilon greater than 0 is arbitrary, therefore, therefore gamma, therefore right hand side is 0, and therefore this modulus is 0, that is modulus of integral c fz dz by z minus z naught minus 2 by I fz naught is 0, not gamma. Fz dz minus 2 pi I fz naught is 0. Modulus of this is equal to 0. This implies this value is equal to 0, and hence it is fz dz equal to 2 pi I f of z naught. and this is equal to my f of z naught equal to, if I divide by 2 pi, then 2 pi I, then this is this one as the theorem. This is z minus z naught. I have forgot to write this one. So this is z minus z naught, z minus z naught. This is z minus z as the proof. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.